Okay, so if there's no external work done, then you can kind of turn it into this total energy before must equal to the total energy after. Right? And that can be very convenient, just like we did with momentum. Momentum before equals momentum after, we have energy before. Okay, so that's what I'm doing here. That's where this came from. This comes from just 0 equals delta K plus delta U. So what energy do we have beforehand? We have kinetic energy from the cannonball being shot from the cannon. There's no potential energy to begin with if I set that as my reference level. One thing you gotta be careful of with using MGH, when we derived MGH, we assumed upward is positive y, which means that from here on out, whenever you use MGH, upward has to be positive y. Just like with the kinematics equations, it assumes constant acceleration, so they only apply with constant acceleration. The same thing here. You can't use this if you say downward is positive y. We did that with the Atwoods, modified Atwoods machine. We kind of flipped them up and down to make the accelerations match. But if you're going to do energy, you can't do that. So, kinetic energy essentially turns into gravitational potential energy, and then you do some math, and you can get something like that. So, the result, this, V naught squared over 2g, that is the same as if you use kinematics.
If this is acceleration due to gravity, would that be negative?
No. G, if you ever have a physics teacher who tells you that G is negative, don't follow their advice. Okay? It's not good because G is just a constant. It's just a number. Whether it's positive or negative is entirely dependent on your reference frame. In this case, the acceleration would be negative g. But there's nothing in MGH that talks about positive direction. It's a scalar value, right? All that matters here is that when we derived this, we assumed that positive y is up, and so this only works with positive y up. If you suddenly make positive y down, then that means that you would gain potential energy going downward. And that doesn't work because it wasn't derived that way. So you got to keep, yeah. So use just G, just 10. There's no direction to G. Okay, don't do that to yourself. There's no direction to G. G is just a number. Okay. So then you solve for H, and you can get something like 5 meters. Okay, so this is like the easiest. Like this is what I have my freshmen doing. Okay, you just take gravitational potential energy, transform it into kinetic energy, and transform it back and forth. Right? That's all it is. How about let's take a similar situation, but let's do it in reverse. Let's say you have a ball that is on a swing or on a rope, and it swings down. Right? It swings down. We want to know how fast it's moving as it swings down. Just to give you a kind of like a hint, there are many ways I could make this question more complicated that are legitimate in the sense that they have been on past AP exams. It would be perfectly reasonable to have this object come down and then hit something else. And you should be able to take that collision and know what's going to happen. I could make it be a inelastic collision. Maybe it runs into a bucket and then the bucket falls off with it. Or I can make it an elastic collision where they collide and they go off at different angles or something like that. You should be able to handle either scenario.
Do we need to memorize the elastic equation that's in the book?
I'll get to elastic collisions in a minute. Okay, so regardless, let's go ahead and apply our energy kind of calculations here. How do we figure out how fast it's moving as it swings down? Again, the only reason why we can say this, you have to make sure that this assumption is legitimate, is that the only forces acting on, or the only forces that do work on our object are conservative forces. So there's two forces acting on this object. There's tension and there's gravity. And tension is always pulling perpendicular to the direction of motion, so tension does not do work. It's not that tension never does work. You can take a rope and you can pull it so that it swings in the direction of the rope. But in this case, it is, if you just have a fixed pivot, it will swing in such a way that tension does not do work, which means gravity is the only thing doing work, therefore it's all potential energy. All right, so now we essentially have it in reverse. This time what I did was I'm going to use the starting height as 0 potential energy just to have you guys practice different kinds of potential energy calculation. So in this case, it is still losing potential energy. It's just going from 0 to a more negative potential energy, right? So how do we do this? You have 1/2 mv squared for the kinetic energy and mgh for the gravitational potential energy. And so then when you solve it out and you were trying to solve for v, you get something like this, a negative square root of a negative 2gh. And when you look at that at first glance, you're going to say, well, that's an impossible answer. It's only impossible as long as h is positive, which should make sense. In other words, there's no solution for velocity if somehow this ball like swung upward. It will never swing upward. It will never gain height. It must lose height. H must always be negative for this to have a real solution. Okay, so in order for this to have a real solution, H must drop 5, or in this case, it drops 5 meters, and then the negatives cancel out, and then you get a real solution. So I guess one thing to be careful of that I kind of foresee students making mistakes is making this a minus mgh, either because you're thinking, oh, g is negative, so it's like negative, or h is negative because it's going downward. If you do that, you better substitute all the numbers in ahead of time. Then that's okay. You know, your h is dropping. It's like a negative height. It shows up eventually anyway. That's okay. But definitely don't just say negative mgh just because g is negative. Because, again, this isn't talking about a vector, right? This is talking about a value, a scalar value, u. That means at this position, at every position, there's some value of u, and you're simply adding what that value is. There's no interpretation of direction here. There's no interpretation for kinetic energy either. It's not like if it's going forward, it's a positive kinetic energy. If it's going backwards, it's a negative kinetic energy. It's just kinetic energy.
Why isn't it just going to the left then? Is it
It doesn't matter because it doesn't matter because v ends up being squared anyway. Yeah. So okay, so you work it out, you get 10, right? So in other words, it's kind of a mirror image of this. Instead of being shot up, it's dropping down. You still have the same amount of potential energy change. It's still changing at height of 5 meters, and so therefore you still get a velocity of 10. Okay, let's try a slightly more complicated problem. Let's say you have a potato and it drops onto a spring. It is a sweet potato.
Oh, it's sweet potato this time. Okay. Last time it was baked potato. Okay.
Yes. So let's say it's dropping on a spring, and we want to know how far. And if you can't see what that says x max. What is the most that it compresses? We want to know how far it's going to compress. I think that's very reasonable. Well, a spring, or it could be like a trampoline or whatever. Something
But it follows that rule.
that is Hookean. It is a Hookean spring. Okay. Hookean. Just Hookean. Hookean. Okay. So what I'm going to do is, it's entirely up to you where you want to choose your 0 gravitational potential energy line. I'm going to choose it to be the top of the spring, where the spring is at equilibrium. But you can choose the very top. The result's going to be the same. If you do your math very carefully, the result will be the same. What once again, just looking at the different forces we have gravity, we have a spring force. That's pretty much it. All the forces are conservative, so we can write a, oops, not that one. We can write a conservation of energy statement, right? The initial energies are equal to the final energies. It's just this time we also have the spring. Spring initial, spring final.
For Newton meters, the like units would
It'd be joules.
would be
This is all joules. Everything here should be joules. So, if we look at where it starts, if it is dropped, okay, if it is dropped, there's no kinetic energy. Starts with that much gravitational potential energy. There's no spring potential energy yet, it's not compressed. And then it just turns into... Now, one thing to point out is that as the spring compresses, by the time it has compressed all the way, it is below the zero gravitational potential energy line. So it needs to drop, right? So what I put here is like a negative x max to indicate that whatever x max is, it is leading to a negative gravitational potential energy here. It is lower, it is below. Okay, it's not the g that makes it negative, it's that it's lower than our zero reference line. And then you have the spring potential energy. So the way I wrote this, okay, and you just have to be consistent in how you do it. You don't have to do it this way. Because I put the negative there, that implies that as the spring compresses, that is a positive x max value. A positive x max value is giving me a negative gravitational potential energy. You can switch this around if you want, but this makes sense to me how I'm measuring what a compression distance is. This is important because as we solve for this, this is a quadratic equation, which means there's going to be two solutions. It's going to be some sort of plus something and some minus something. And so because I'm saying that I want a positive x max value, it's going to tell me to use the plus something instead of the minus something. Huh?
Why is
Oh, 1/2 kx, because that is the potential energy from a spring.
And the reason why you are getting both is because it's telling you, hey, you also get the same potential energy if you stretch the spring this way.
Yeah. Yeah, actually what this is taking into account is either you can compress it and you lose more potential energy, or you could gain a little bit of potential energy and then you won't stretch a little bit less up. There's two, yeah. Say again? Oh, well, think of jumping on a trampoline. When the trampoline has come down to its lowest point, how fast are you moving?
0?
You've never been on a trampoline? You're not moving, right? Yeah. So zero kinetic energy. Yeah. Okay. The other thing that this actually kind of tells you, to be honest, is, well, we'll get to it in a second, actually. Okay, so if you do the quadratic equation all the way out, you can get the symbolic version on the right, or you can get the, you can do it on the left-hand side with the numbers. I want to investigate this real quick, actually, because it's really interesting. All quadratic equations are symmetric, right? It is mg over k plus some value and then minus some value. So in other words, inherently, there is some amount of stretch involved with having the potato on the spring. How much will the potato stretch if I put it on the spring? It is, if you look at putting the potato on the spring, puts it at a new equilibrium position. The new equilibrium position would be sum of the forces in the y equals to force of gravity minus, or sorry, the other way around. Force of the spring minus force of gravity equals to 0. That would be like the new equilibrium position. So you have negative kx is equal to fg, or sorry, not k, negative kx, just kx. mg, x equals to mg over k. So, in other words, what this mg over k is showing is that once the potato hits the spring, there is a new equilibrium position where it's going to oscillate around. It doesn't actually oscillate around this 0 point. It's going to oscillate around a slightly lower 0 point. And then from there, it is symmetric in how it's oscillating above and below that new equilibrium point. I think it's really interesting that this mg over k showed up without ever using Hooke's law, right? Nowhere in here did I use some sort of kx equals to fg or mg. But it's actually inherent in the fact that 1/2 kx squared was derived from kx. And so, I don't know, it's kind of neat. I always think it's interesting when like calculus and stuff shows up in like not calculus things, because calculus is everywhere. Okay, so you calculate all the way out, you get something like this. So in other words, based on the mass that I used, based on the spring constant that I have and all that stuff, the potato will hit the spring will compress. It'll have a equilibrium height that is 1/5 of a meter below its original top height. And then from there, it will oscillate up and down about 1.4 meters from that spot. Right? This tells you how much above or below it will have its maximum compression or expansion. So it will compress a maximum 1/5 of a meter plus 1.4 meters, or it will then go in the other direction, 1.4 meters, and it'll just go. Right? Another way to interpret that is all of the gravitational potential energy goes into this much stretching of the spring. Really. Yeah. Okay, we've got 10 minutes left. I still need to get to elastic collision. So, questions on this? So, any question I feel like should be fair game, like springs and falling and flying and moving and colliding. Yeah. X max is a measure of how far from here, the original equilibrium position, down it will go. So it will stretch a maximum of like 1.6 meters down from where it started. Okay? All right. The next page has just a lot of stuff, so I'm going to need like that. Yeah, I mean, I can upload, I can scan this and upload it, and that's fine. Plus, it's being recorded, so. All right. So, as I look at elastic collisions and inelastic collisions, here's how I'm describing both. The left-hand side, I started thinking about perfectly elastic, and I changed my mind. So this is an inelastic collision. Now, I call them perfectly inelastic. I think on the AP exam and in the textbook, they just say inelastic. What's implied by inelastic is that you have two objects that are separate, and then they combine, and they stick together. Right? That is inelastic. Elastic, I prefer to call them perfectly elastic, but again, you may not necessarily see the perfectly part. Means that not only is there a collision that conserves momentum, but your kinetic energy stays constant. Okay. Now, it may be tempting to ask, how come kinetic energy isn't constant all the time? Why is it only a perfectly elastic collision? Why can't it happen here? Well, we can analyze this situation for the energy that is involved. If we look at the momentum and then we look at energy, you get something like this. Initial momentum is equal to the final momentum, which means that the final velocity must equal something like this. Conservation of momentum is always true. It can never not be true. This is not conservation of energy, because there's nothing in here about potential energy or other types of work. This is just kinetic energy, and there's no law that says that kinetic energy must be conserved. Just energy is conserved, not kinetic energy is conserved. So this is actually a very special case. But anyway, so if we look at the kinetic energies before and after, here's the kinetic energy before. It's just this object moving. Here's the kinetic energy after. They've stuck together, moving at the same velocity. And if we substitute from our momentum information into the kinetic energy here, we get something like this. Right? You still have the 1/2 mv m1 plus m2 squared, or sorry, m1 plus m2. But now I substituted the m1 v naught over m1 plus m2 into the whatever. I substituted it in here. You're squaring it. When you square this, what do you get? You get 2 of these m1 plus m2s on the bottom. One of them will cancel with that. So you have one of these in the denominator. You have an m1 squared, and you have a v naught squared. So you get something like this. Ignore this for now. Ignore this for now. Go back to that. Okay. So double check me on my math here, but right? One of these is going to cancel with one of these, leaving only one of these on the bottom. You have the m1 squared, you have the v naught squared, you have the 1/2, right? Okay. So what we want to do is we want to compare the initial kinetic energy to the final kinetic energy. How are they not equal? Well, what terms are they different? This has m1, this has this big middle term. If we think about that middle term, m1 will always be greater than or equal to this term. Let's think about that for a second. Think of the extreme case when m2 is 0. It runs into nothing. Runs into like a coffee filter. Something really, whatever. Something really small. Then m1 squared over m1 is m1. But if I start adding anything at all to m2, is now being divided by a larger denominator, which means this will always be less than m1. Because you have any sort of m2 there, you are now losing energy. No. Not as far as I know.
Not how we're doing.
There is no physical object that we found in the universe that helps you speed it up when you push it, that has a negative inertia. There's nothing that, you know what I mean? Well, I hope you do, because that would be like our, well, that would be an unstable situation though, right? That means that if you push on something, it wants to continually go faster and faster, as opposed to resisting changing in motion. Anyway, okay, so what about elastic collision? In an elastic collision, you have a scenario where the two pieces don't stick together. They actually break apart, or they stay apart, and the initial kinetic energies have to equal the final kinetic energies. I don't want to derive the equations. They are derived in your book on page 266. They skip a few steps, so what you end up having to do is you're going to substitute somewhere in here, but it ends up being a binomial, so you have to expand it, and you get this like kind of complex quadratic. But when you work it out, it actually simplifies to just these two equations. So I want to make sure you understand what you're looking at here. This is the velocity of the first object after collision. This is the velocity of the second object after collision. So this is for that guy, and then this is for that guy. Right? This guy for that guy. So Without taking a little time, these just look like any other equation, but they're not. It's very useful to look at the extremes for each of these. Let's take a look at what happens to the first object. What if the second object is much smaller than the first object? Okay, if M2 is much smaller than M1, you essentially have M1 divided by M1, which means that your velocity doesn't change. The first object just bulldozes right through, right? Truck runs into spider. Truck does not change speed. What if they're the same mass? So this would be like two billiard balls. One billiard ball runs into the other. What happens when M1 equals to M2? M1 minus M2 equals 0. So what you have is you see Newton balls where they kind of go like this? That's exactly what's happening. You have a perfect transfer of momentum and energy from one object to the next. And this is a range, right? So in other words, in between here, the behavior is in between. The first object goes from maintaining a speed to slowing down as the second object gets more massive until they match mass, and then the first object will stop. Assuming perfect elasticity.
Which is no such thing.
That's not that there's no such thing. It is when the interaction is at a minimum. Think of an ideal gas. What makes an ideal gas? It's usually low pressures, low temperatures, low interaction. Right? Okay, what happens if the second object is really big, like a tennis ball hitting a wall? It reflects. It will reflect. Because if you look at the equation, when M1 is much smaller than M2, it's like a negative M2 over a positive M2. It's like a negative 1. So it's just perfect reflection.
It's like a wall, like a ball hitting the wall.
Yeah. Yeah. Okay, so what happens to the second object? 1 second. Okay, what happens to the second object? This one is the most interesting consequence. If the second object is very small compared to the first, look at what happens. If M2 is really small, you have 2M1 over M1. It means there's an upper limit to a collision. If you have a truck run into a tennis ball, the tennis ball won't just fly off at infinite speed. It actually can at most fly off at twice the speed of the original object. Which means that tells you something about a baseball player hitting a baseball. You want him to, he needs to hit it at the very tip of the bat to get the maximum velocity of the bat to get twice that velocity on the ball in order for it to go as far as possible. If, assuming of course it's essentially an elastic, a perfectly elastic collision, right? So that tells you something about, how do you analyze kicking something as far as possible, hitting something as far as possible. It has an upper limit. And then the other stuff is should make sense. The wall doesn't move. Okay, so tests next class.
How much power is going to be on the test?
How much power is going to be on a test? A very easy amount.
Unlimited power.
The door is right there.
Those are only if one of the things isn't moving, right?
It doesn't actually matter because anytime something is moving, you can choose a reference frame where it's not moving. If you want to know, if you ever ask for how fast is it going, use F. If it asks for, if it asks for forces, then you use forces. But otherwise, sometimes if it asks for how much it displaces, you have to look at whether it's actually stationary. Then can you balance it? Otherwise, it's probably they'll say something like, yeah. Does it really take that much time?
It does, mostly because I have to do 16 different mission statements for all the colleges that I'm applying to via the arts department.
No, I mean not the college apps. I mean posts, literacy posts.
Yeah.
It should only take like
Took me like an
10
hour the
minutes.
last time.
Why? You pick an article, you read through it, and you're like, hey, that's cool. Or watch a video. See, the thing is, if I let you do it, I gotta let everyone do it. You do it.
So no.
I want to say no because you've had like a whole month to do it. So I can't imagine there's any excuse where in an entire month you couldn't have devoted half an hour to do this thing. It's not like I just gave it to you and I gave you 3 days to do it.
Yeah, yeah. No, that makes sense.
No.
Okay. Do Thursday night.
Actually, I think I have it set for maybe tomorrow. I might have set like a midnight cutoff or something like that. You should look at it. It tells you what the due date is.
Okay.
I set a due date on it.
Solid. Thank you.
Yeah. What's up?
Do you know what voltage is?
Should be in lower north, 123. I want to walk through some of the equations that are on the. Hey.
You know where Justin went?
I have no idea.
Okay. Thank you, though.
Yeah.